Good morning. This is your stats sensei, Mr. Spencer, looking to go over test corrections for proportions. Please remember, you need to write down the problem number, the letter answer, and if it's in red, you'll need to write that down and anything else that I write down for your corrections. All right, and this video will cover problems 1 through 10. So USA Today reported that speed skater Bonnie Blair had won USA's heart, according to a USA CNN Gallup poll conducted on the final Thursday of the 1994 Winter Olympics. When asked who was the hero of the Olympics, 65% of the respondents chose Blair, who won 5 gold medals. The poll of 615 adults done by telephone had a margin of error of 4%. Which of the following best describes what is meant by the 4% margin of error? Well, remember, margin of error, if we were writing down our formula, which you'll need to write down, it would be P hat plus or minus Z star P hat Q hat over N. And the part that I'm circling is the margin of error. Okay? And so it's how far it might stray from that 65%, right? It's how far it might stray from that 65%. So margin of error is a distance from the sample proportion, so from P hat, that we can expect the true population proportion. So we would not expect it to be lower than 0.61, and we would not expect it to be higher than 0.69. We expect it to be no more than 4% away from the 65%. All right, number 2, suppose that public opinion in a large city is 35% against increasing taxes to support the public school system. In a random sample of 500 people from the city are interviewed, what is the approximate probability that more than 200 of these people will be against increasing taxes? Which of the following setups would answer the question? Well, essentially what we're looking for is a binomial, but we'd be looking for a binomial that would be, we would say, we have a random sample of 500, what's the probability that more than 200? So we want the probability that X is greater than 200, and we have 500. So really, if we were doing this as a binomial, we would go, you don't need to write this down, but this is for understanding purposes. We would want 500 choose 201 and 0.35 to the 201 times 0.65. 500 minus 201 is 299, plus plus 500 choose 500, 0.35 to the 500th times 0.65 to the 0. So we would need something that looked like that, and we don't have anything like that. We do have binomials. A and B are both binomials, but we need a CDF, not a PDF. So in this case, we're going to have to use a normal approximation. With a normal approximation, our formula is P hat minus P, PQ over N, where P is the population. Okay, so in this case, we had a sample proportion of 0.40, and P, and you need to write this down, P in this case is 0.35. So we use the sample proportion, the population proportion, and please remember, these two values have to be the same. All right, we always use the population proportion in the denominator. We do not use the sample proportion in the denominator. So standard error for a hypothesis test always requires that you use the population values. All right, number 3, the manufacturer of balloons claims that P, the proportion of its balloons that burst when inflated to a diameter of 12 inches is no more than 0.05. All right, so basically their claim is, remember, our null hypothesis is always going to be equal, so their claim is HO P equals 0.05. Some customers have complained that the balloons are bursting more frequently. Oh, so they're saying it's greater. So they're saying that it's actually greater than 0.05. All right. So if the customers want to conduct an experiment to test the manufacturer's claim, which of the following would be appropriate? Well, what would be appropriate? The first HO, the null, is always equal. In this case, they're complaining that it's happening more frequently. If it happened less frequently, they'd be happy. So they're complaining that it'd be more frequently, and that would be the key phrase there, more frequently. All right, so looking at number 4. A consulting statistician reported the results from a learning experiment to a psychologist. The report stated that on one phase of the experiment, a statistical test result yielded a p-value of 0.24. Well, we should be thinking about that. That is a large p-value. It's definitely larger than a normal alpha, which was normally 0.05. So if the p-value is greater than 0.05, typically we're going to fail to reject. We'd have to have a very, very odd alpha if that's were the case. So based on the p-value, which of the following conclusions should the psychologist make? Well, p-value is a probability of getting a test statistic as extreme or more extreme, given that the null is true. We will reject when the p-value is small, usually less than 0.1 or less than alpha equal to 0.05. So one of those. So in this case, we're going to fail to reject, which means we're going to say it's not statistically significant. So not statistically significant because if the null hypothesis were true, one would expect to get a test statistic at least extreme as that observed 24% of the time. All right, so there's a, all right, so basically that's where we're at with that one. In a large school district, 16 of 85 randomly selected high school seniors play a varsity sport. In the same district, 19 of 67 randomly juniors play a sport. A 95% confidence interval for the difference between the proportion of high school seniors who play a varsity sport is to be conducted. What is the standard error of the difference? All right, so we are looking at a confidence interval. This is really important. So we need to write down the confidence interval formula, which is p hat minus p1 minus p2 plus z star, and this is my standard error. So the part that we care about in this is this part right here, because that part represents our standard error. So when we plug into that formula, we have 16 over 85, and then of course that's 69 over 85, and that came from 16, that's 85 minus 16 equals the 69. Then we have 19 over 67, and of course that 48 is the 67 minus the 19. So then we're going to have to solve this by hand. So you're going to get to plug that in the calculator, solve it by hand, and that will give you this value. Okay? All right, next problem. In 2009, a survey of internet users found 79% of adults age 18 and older in the United States use the internet. A broadband company believes that the percentage is greater now and that than it was in 2009 and will conduct a survey. The company plans to construct a 98% confidence interval to estimate the current percent and wants the margin of error to be no more than 2.5 percentage points. Assuming that at least 79% of adults use the internet, which of the following could be used to find the sample size needed? Well, so if I were actually starting off with a hypothesis test, the hypothesis would be P equals 0.79 because that's what they said was the claim. Well, they're checking to see that it is actually more than that. But regardless, this is my claim. And because that's my claim, that's what I'm going to use when I plug into the formula. And please remember, the formula for the confidence interval is going to be p hat plus or minus z star p hat q hat over n. Well, since we have an initial claim, we're going to use that. And this right here equals the margin of error. Well, they're saying the margin of error in this case is 0.025. So this part under the parentheses has to be equal to 0.025. We have the 0.79, and then we just need to verify our z star. All right. So when we're going about verifying our z star, it's second vars, inverse norm, parenthesis, 1 minus. In this case, we wanted a 98% confidence interval. That was right here. 0.98, close parenthesis, divide by 2, mean of 0, standard deviation of 1. And there we get our 2.33. Okay? All right, so that's how we got 6 being D. Moving on to number 7. A researcher has conducted a survey using a simple random sample of 200 registered voters to create a confidence interval. So we're starting off with 200 to create a confidence interval to estimate the proportion of registered voters favoring the election of a certain candidate for mayor. Assume that a sample proportion does not change. Which of the following best describes the anticipated effect on the width if the confidence interval, if the researchers were to choose a sample of 50 rather than 200? So first off, if n goes down, the width increases. Right? If n goes down, the width increases. Well, I gave this formula in the notes where it said 1 over new over original. So in this case, our original was 200 and we're going to 50. So now we have 1 over, and this 50 over 200 reduces to 1/4. So this ends up being 1 over 1/2, which equals 2. So the width of the new interval would be twice the width, because as n went down, the width increases. All right, very important to write that down. Width goes down, and n goes down, width increases. The opposite is also true. As n goes up, the width decreases. So a survey was conducted to determine what percentage of college seniors would have chosen to attend a different college if they had known then what they know now. In a random sample of seniors, 34% indicated that they would have attended a different college. A 90% confidence interval for the percentage of all seniors who would have attended a different college is given here. Well, please remember, the formula is p hat plus or minus z star p hat q hat over n. So in this case, we're looking at 0.34 plus or minus, and we'd have to calculate a z star, but we don't need to do that because the calculator is going to do this for us. But this is our formula that we're plugging in. When I go to the calculator, I go stat test, drop down to 1 proportion z test. Oops. Stat test, 1 proportion z test. And I'm going to plug in, I'm sorry about that, stat test, not 1 proportion z test, 1 proportion z interval, which is letter A, so 1 proportion z interval. And my x values, they start off right off asking for the x. Well, remember, p hat equals x divided by n. Well, p hat's 0.34 and our sample size is 100. So I can basically go 0.34 times 100, sample size of 100. And we wanted a confidence interval of a 90%. And we end up getting 0.262 and to 0.4172. All right. Okay, number 9. A planning board in Elm County is interested in estimating the proportion of its residents that are in favor of offering incentives to high-tech industries to build plants in that county. A random sample of Elm County residents was selected. All of the selected residents were asked, are you in favor of offering incentives to high-tech industries to build a plant in your county? A 95% confidence interval for the proportion of residents in favor was calculated to be 0.54 plus or minus 0.05. So we have this 0.54 plus or minus 0.05. Well, what that really means is my interval could be as low as 0.49 and as high as 0.59. So we're 95% confident that the true population lies between 0.49 and 0.59. So we are 95% confident that we captured the true population. We're 95% confident the true population lies within the interval 0.49 to 0.59. Well, at the 95% level, the estimate of 0.54 is within 0.05. It's no more than 0.05 away from the true population. All right. So 0.05, that is what we're saying that margin of error is. It's how far the p hat might be from, or how far the true population might be from the p hat. And it's not more than 5 below, and it's not more than 5 above. Okay. All right. So moving on to number 10, which will be the last one for this video. So the university will add fruit juice vending machines to its classroom buildings if the student body president is convinced that more than 20% of the students will use them. A random sample of N students will be selected and asked whether or not they would use the vending machines. A large sample test for proportions at the significance level of, and doesn't give what it is, will be performed. The null hypothesis that the proportion of all students who would use the vending machines is 20% will be tested against the alternative that more than 20% of the students will use it. So they're basically saying, okay, HO P equals 0.2, and our alternative is P is greater than 0.2. For which of the following situations would the power of the test be the highest? Well, power goes up when N goes up, all right? And power also increases if the percentage is farther away, all right? So the larger the sample size, the greater the power. So that takes care of power goes up, N goes up. Given the correct direction, the farther the actual is from the claim, the greater the power. So we have to be above 0.20. The one that's farthest away and above 0.20 will be correct. So 50 is farthest away and it's in the correct direction. So E is my answer. It would be my greatest power. All right. We'll catch you on the next one for 11 through 20. Thanks for watching. See you next time.